Hello everyone, happy Pi Day. In this video, we're going to be solving a puzzle that uses pi in a different way. So, as you know, March 14th is celebrated as Pi Day and teachers are usually assigning puzzles or presenting puzzles to their students, so on and so forth. So we're gonna continue that tradition. So in this puzzle, we have the square root of a 3-digit number, pi, which is pi I-E. So pi, I, and E are digits. And then on the right-hand side, we have the square root of pi plus E. Now, this could be a little misleading on purpose because pi is an irrational number, right, as you know. And it goes on forever without repeating. That's what it means. And how do you take the square root, right? When you take the square root, you get another irrational number, which goes on forever without repeating. So how are you able to add those two things and get the square root of another number? Well, maybe PIE, which is a 3-digit number, when you square root it, if PIE is not a perfect square, then its square root is also going to be irrational. So can we have an irrational number equal to another irrational number plus a digit? I think it's quite possible, but that's not the case. Why? Let me tell you. So here's what we mean by this. I know this is kind of a tiny bit misleading. This pi is actually not the irrational number, famous pi that you know. We're going to spell it differently. Well, actually, how do you spell pi, right? You can spell it like this, but that's not the pi we're talking about. We're going to spell it as pi. So the actual equation is supposed to look like this. The square root of PIE equals the square root of PI plus E, where P, I, E are all digits, which means 0 through 9. Now, why is it that way? And why is this a little bit ambiguous? Because it's more fun that way, right? So anyways, here's our puzzle. And we're going to be solving for P, I, and E. How do you do that? Well, there's a couple of ways to go about it. I'll be presenting both methods. Actually, we could probably talk about 3 different methods here. So let's start with the first one. The first method basically involves looking at it from a purely algebraic perspective, which is, what is the square root of a 3-digit number? First of all, what is a 3-digit number? How do you decompose it, right? So you can basically write this number as 100p plus 10i plus e. Okay, great. Let's go ahead and square root that. And on the right-hand side, we can write the 2-digit number as 10 pi plus i. And e is just e. And then, since we're trying to simplify this, we would normally square both sides, right? Let's go ahead and square both sides. This gives us 100p plus 10i plus e. The left-hand side is easy. Right-hand side is a sum, so we're going to square the first term. We're going to square the second term. And then we're going to do the 2ab thing, 2e multiplied by the square root of 10p plus I. Great. Now, here's the thing. The left-hand side is a 3-digit number now, right? But the right-hand side looks like a 2-digit number because of the 10p plus I, but we're adding more numbers to it. So this is pretty interesting, actually. You take a 2-digit number, you square root it. So there's a couple different ways to go about it. For example, the square root of a 2-digit number can be what? For example, what's the square root of 81? 9. It's a single digit, right? What is the square root of 25? 5, single digit number. So this is probably going to be a digit, right? Don't you think? And then we're adding another digit to it, and then we're squaring it. And we're hoping that this whole thing right here, right? We want that to be a 3-digit number, of course, with the addition of this one, right? So you can look at it this way too. Okay, I have a 2-digit number plus, or let me put it this way, square root of a 2-digit number, which is a single digit. So we have a digit plus another digit squared, and that's supposed to be 3 digits. Is that possible? Absolutely. As long as these 2 digits add up to a 2-digit number, right? For example, if you add 5 and 4 and square it, you're going to get a 2-digit number because this will be 9 squared. But if the sum is greater than or equal to 10, so let's say 7 and 8, then its square is going to be 3-digit number. And that's what we're looking for exactly. Does that make sense? So that kind of gives us some restrictions about the values of P, I, and E, particularly E, because E cannot be too small, right? For example, if E is 1, actually this could be possible, right? If E is 1 and the other number is 9, then we could get 100, but do you think it's going to equal 100? Because that would mean if the left-hand side is 100, that means I and E are both 0, which we know is not true, because we know that E cannot be 0, right? Probably not. Okay, so you can kind of eliminate some of these cases. But when you look at it, you could also bring these over to the left. That's going to give you 90p plus 9i, which is kind of like, you know, a multiple of 9, which might be helpful. And bring the e over to the other side. And guess what? You can factor out an e here. I don't know if it's going to be helpful, but that's one way to look at it. So factor out a 9, 10p plus I. And notice that this is actually the 2-digit number times 9, right? So we're looking at a 2-digit number times I. And we can now factor out an e here. That will give us e minus 1 plus 2 times the square root of the 2-digit number again. So notice that this 2-digit number repeats, right? So that might be helpful if you call that number x, or even the square root of that number x, right? Then you'll get an x squared. So you'll end up with something like this, 9x squared. Just notice that square root of the 2-digit number is equal to x. You're going to get something like e times e minus 1 plus 2x. So we have two variables, and it's not super hopeless because you can just kind of test some different cases, right? But anyways, no matter what you do, this is going to be a little complicated, or maybe there's something that I'm not seeing. Okay, e could be 3 or 9 in order for this to be divisible by 9. Is that necessary? I don't think so, because this could be a multiple of 9. Anyways, you can continue with this path because I'm going to show you something else. Now, another way to look at it, which I think was initially meant, is different. So why don't we, instead of just looking at this algebraically, because it's like a brute force method, right? It gets complicated. Why don't we just look at it this way? Okay, we have two perfect squares, and to make it a little nicer, I think we can write it like this too, right? Anyways, so we're subtracting the square root of a 3-digit number minus the square root of a 2-digit number, and now we're getting a single digit from there. So you can look through the cases. Now take a look at this. This number is a perfect square. So which 3-digit numbers are perfect squares? I'm going to exclude 100. Is that okay? Because I don't think I and E both can be 0. Imagine if I and E are both 0, basically you're saying that the 3-digit number and the 2-digit number are the same, which is not true. So obviously I does not equal 0, which means 100 is not going to work. So I'm going to start with 11 squared. 11 squared is 121. And then I'll continue down the list. Let's go ahead and write the perfect squares. You probably memorized them, right? Did you? If not, please do. At least you should know 11 through 20. I'm assuming 1 through 10 you already know, okay? Anyways, 14, 15 is going to be 225. 16 is going to be 256. 17 is 289. 18 is 324 and 361, and then 400. I don't think 400 is going to work, again, for the same reason. I and E both cannot be 0. Okay, great. So those are the candidates we're going to look at. Not a big list. It's not huge, right? But still a long list. But wait a minute. PIE is a perfect square as well as PI. So here's the interesting part. You can actually go ahead and look at the first 2 digits, from the left. For example, is 12 a perfect square? Nope. So this number is not going to work. Is 14 a perfect square? Nope. Is 16 a perfect square? Yes, so this might work. How about 19? Nope. 22, that's what I meant, 220. Nope. 25, yes, this is a candidate. 28, nope. 32, nope. And 36, yes. So we have 3 candidates. Guess what we're going to do? We're going to test them because there's only 3 options, right? 3 choices. So if our number is 169, now take a look at this. Is this going to work, right? That's what you need to check. Question mark. Or is this going to work? 256 minus 25, is that equal to e, which is 6 in this case, question mark again. And for the last one, 361 minus square root of 36, is that equal to e, which is 1? Okay, we're going to check each one of these and see which one. Maybe we're going to have more than one solution, right? So this one is, let's see, we'll number these 1, 2, 3. And then the first one is going to be 13 minus 4, which is equal to 9. Beautiful. So this checks. Second one, 16 minus 5 is equal to 6. Nope, doesn't work. Number 3, remember 361 is 19 squared, so it's going to be 19 minus 6, which is equal to 1. Nope, again. So we end up with a single solution. So what is that supposed to mean? It means 169 and 16 are the values. If you're wondering, because PIE is 169, if you really want to write the solution, P equals 1, I equals 6, and E equals 9. And that will be the unique solution. Okay, let's look at the third method, which is very similar to the second one, by the way. First method is brute force. You don't want that, but at least we tried. With the first method, the third method, we're going to look at the following. Instead of going off of the 3-digit numbers that are perfect squares, why don't we focus on the 2-digit numbers that are perfect squares? For example, 3 squared is 9, so it's not going to work. 4 squared is 16. 5 squared is 25, 36, and then 6, 7, okay, 8, 9, and that's it, okay? So these are the candidates, okay? So here's the trick. We're going to add another digit here, and we want to come back with perfect squares. Is that possible? 1, 6, 9, yes. 2, 5, 6, yes. 2, 6, 3, 6, 1, yes. The others don't work. You can test, but it's not going to work. So we have 3 candidates again, but I think we arrived at these a little faster, don't you think? Okay, so from these, you can easily check because you have both numbers. And happy Pi Day again. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out aplusbi and SyberMath and aplusbi, and bye-bye.